Hello, this is Theresa Stack, Associate Professor at Montana Tech, and this lecture will cover different types of sampling techniques and sampling methods, and we'll start to get into some basic exposure calculations. The objectives of this learning unit will be to review different objectives for our sampling strategies and our sampling protocols, an introduction to various types of sampling methods and broader categories of sampling, and an introduction to exposure assessment, or for some of you, it'll be a review of our exposure calculations. So why do we sample? There are different objectives for sampling. We do it to evaluate health risks or to answer the concerns of workers, of course, for compliance and litigation purposes. We do it to choose or evaluate the effectiveness of our personal protective equipment, engineering or administrative controls. We also sample to establish work zones, similar exposure groups, or for epidemiological studies. Our rationale for occupational sampling or airborne sampling is inhalation is typically the primary route of exposure. At least it's the one that's most understood, as opposed to dermal exposure. Most occupational exposure limits are based on airborne concentrations, and this is often used as a starting point or a point of reference. It's easier than biological monitoring and less evasive to the worker. We use our inhalation exposure monitoring as a surrogate for absorbed dose. And again, of course, it's non-evasive to the worker. So as a review, what is the difference between an exposure and a dose? Exposure assessment is the central focus of our occupational safety and health programs, whether we're looking at exposure monitoring, employee training, hazardous communications, different types of specific programs, whether it's machine guarding, radiation safety, or hearing conservation. But the assessment is the central to why we embark on putting programs in place. So we remember there are different routes of exposure for which a dose is assumed. We can have inhalation, dermal exposure, ingestion, injection, and then that physical route of exposure. And the physical state of the agent or substance, the route of exposure, and the overall objectives, why we need to sample, will determine which type of sampling plan that you choose. So before we begin, let's just get a scope of what's this word sampling. Let's get an idea of what we're doing here. And I always like to bring it back to the background of scientific inquiry. And so sampling is a process for which we take a number of predetermined observations, we pull them from some larger population, we use a method of obtaining data from them, and we hope that we can generalize the results back on that larger population. So sampling, the techniques that we do are very important given what our objective is. Is our objectives worst case sampling? Is our objectives periodic sampling? Are we evaluating a chemical or an exposure that we already know is there? Or are we trying to determine if there's a new agent or a new level that we need to be concerned about? So different ways in which we choose our sampling population can be randomly or systematically. And always this observation sampling is going on when we're doing different types of occupational or environmental monitoring. So let's start with two broad categories of sampling which are used to answer the question of where do we sample. So we have two main zones for which we sample in. We sample in our personal zone, whether that's our breathing zone or our hearing zone. That's typically integrated and or continuous monitoring. But there's also a lot of area monitoring that takes place, and this is another form of sampling. And whether that's surface sampling or bulk sampling. So our two main zones are personal and area. So our personal sampling, here we can see a worker who's wearing a pump. The pump is actively pulling air through a sampling cassette. This is active personal sampling. We try to have the sampler right in the worker's breathing zone. This is another form of personal sampling when you're wearing a dosimeter. So they do read out in real time. This would be direct reading personal sampling, but this would be passive. Passive because air isn't being actively pulled through the medium, although air does have to pass through the medium. So we have some new definitions here. We have our personal sampling in the breathing zone or in the hearing zone. We have active sampling. A pump is actively pulling the air through some form of sampling media, which is this filter cassette in this example. And then we have passive sampling. And this is also direct reading. We can directly get our results from this type of personal monitor. And this is considered passive sampling. Passive because you don't have to use a pump. It doesn't need any calibration. And personal sampling is a direct connection of monitoring a worker within that zone of exposure. So our second type of zone sampling would be area sampling, or it's also called bulk sampling. And when we sample thermal exposure, so we sample humidity or wind speed, we sample light intensity, we sample heat index, this is a type of area sample that we then interpolate to a person's exposure category or their exposure matrix. But area samples are taken primarily in a fixed location and represent the potential risk from airborne contaminants or agents that are in this area. So in this picture, this is an example of a photoionization detector, a PID, and this is a direct reading instrument which could be used to directly read an area for potentially oxygen or hydrogen sulfide or carbon monoxide. And so this isn't personal sampling, but it's area sampling. They're usually done in conjunction with one another. And bulk samples are used to verify if certain constituents are present, and if so, in what concentration. So then we can narrow down our personal sampling and be more specific. And then finally, there's surface sampling. Surface sampling can be seen as a type of bulk sampling. It evaluates levels on a specific location. It is considered a wipe sample, not a swipe sample. We'll remove that typo there. And or it can be done with direct reading instruments. For example, if there's lead in a paint, or I've even seen some surface beryllium readers. Or you can do a wipe sample, for example, the mold in the picture, and then send it to a lab for later analysis. Maybe cadmium dust in a work area is something else that you can sample for. So how do we sample? Well, we have different types of sampling protocols. The main one that we typically use, but not always, of course, in aerosol or airborne concentration sampling is integrated or continuous monitoring over a full shift. And we can do this actively with a pump or passively with a badge of some kind. We can do random sampling throughout a shift, so we just pick a time period in which we may choose to sample certain points in time, beginning of shift, after lunch, end of shift. We can do it systematically, for example, during a specific operation. Maybe that would be our worst case sampling. Or we can randomly sample. We can randomly sample who and when we sample. And always along this continuum of either systematic or random sampling, we're doing our observational sampling, right? Because we're seeing the people at work, and we're going to try to integrate this somehow with our different types of techniques. So integrated or continuous sampling, it's a collection of a sample over a prolonged period of time from several minutes to several hours. We can take one sample for an 8-hour period, or to get more specific data, we can take multiple samples for an 8-hour period. We can randomly sample throughout the shift. It should be noted that most occupational exposure limits assume an 8-hour work shift, and so they like us to sample over an 8-hour period so we can take a look at a worker's average exposure or their time-weighted average exposure. And this is used to calculate a worker's daily exposure to hazardous substances or agents, taking into account the average level of a substance and the time spent in that area. So there's two different calculations that we can use. We can take our concentration times time, or all of our concentrations times the time we sampled, and divide that by 8, and that'll give us our 8-hour time-weighted average. Or what we do more specifically in industrial hygiene is we take our concentration times time, so our concentration that we found when we were sampling, weighted by the time that we took that sample, and we put that over the sum of all of our time. And this may give us a different exposure profile than we had if we averaged it over an 8-hour period. So there's this actual time-weighted average and this 8-hour time-weighted average. So this would be an opportunity to review these calculations and do a short example. Our problem. What is the 8-hour time-weighted average? So our formula for an 8-hour time-weighted average is the sum of concentration times time over 8 hours. So we have concentration times time, concentration times time, and now we'll multiply. And sum. I apologize for my phone calculator. I can't find my other one at this moment. And our units are parts per million hours. And we put this over 8 hours. And our 8-hour time-weighted average is 2.81 parts per million. Weighted average. And our formula for our actual time-weighted average is the sum of concentration times time over the sum of time. So I still have my same calculation time formula here. 3 parts per million times 2 hours, 2 parts per million times 2 hours. And when I add these together, I'm going to come up with the Same answer as the previous problem, 22.5 part per million hours. So this is my total. But now I need the sum of time. And that would be 2 plus 2 plus 2 plus 1 plus 0.5 equals 7.5. So we only sampled for 7.5 hours. And of course our hours cancel out there. And now our actual time-weighted average is 3 parts per million as compared to our 8-hour, which diluted that last half hour and assumed there was no exposure. One of the reasons why we tried to sample as close to our 8-hour period as we can. So let's do one more calculation together, and this would be to convert parts per million to milligrams per meters cubed, or to go back and forth the other way, whichever way we need to go. Now we're assuming that we sample near normal temperature and pressure, and therefore we could use the following. Okay, so let's convert our concentration in parts per million to milligrams per meters cubed. And I may set this up differently than you would. I am only now starting to understand the Common Core. So I'm going to use this 3 parts per million. And I'm plugging it into this equation, assuming I had carbon monoxide whose carbon dioxide, whose molecular weight is 44.0095 grams per mole. So here's my unknown. And this does, of course, assume that we're close to normal temperature and pressure. Okay, so I need to isolate this variable. I'll do that first by getting rid of my bottom number. Again, I apologize for my calculator. 3 times 44.0095 equals 132.02 equals milligrams per meters cubed times 24.45. And I need to bring this over through division. So now I have the answer of 5.39 equals my milligrams per meters cubed of CO2. And I was able to convert from parts per million to milligrams per meters cubed just by simply plugging it into the equation. Passive versus active sampling. Active sampling, most sampling techniques use active sampling. That's energy draws air or the contaminant through a pump across the media. And the energy can be battery operated or somehow manually. So for example, when you use a Draeger tube, you're manually pulling air, and this is active sampling. So here's our sampling media. The air is being pulled across the media into the pump and is then, of course, filtered and discharged. And the sampling contaminant should be deposited on our media. This should be as close to the breathing zone as it could be. Up on the shoulder would be a little better. versus passive. Passive sampling is neither electrical or manual. The only air movement that is required is that it's on the outside of a person's clothing, and it isn't impeded by air movement. So, for example, putting it under a hoodie wouldn't work. But this is passive sampling, and this is active sampling with our pump. And then observational sampling is when we observe people's behaviors, for example, repetition, poor work technique, posture, and this can be integrated into a formula or it can be a snapshot in time. And here is a picture of observational software that I use when I evaluate somebody at work, and then I would take these video snapshots and put them into the biomechanical analysis program and come up with an integrated sampling exposure. So who to sample? Well, we try to sample in each of our representative job locations. We can take subjects with the highest suspect exposure to get an idea of what their exposure is, or we can do random sampling, and certainly one of the first or second homework assignments that you'll do will be an exploration of this random versus worst case versus systematic sampling. And of course, most industrial hygiene programs include all of them. And it's usually not cost effective, or it certainly isn't necessary to sample everybody. But remember, when we are sampling, we are drawing some proportion of the population. We're taking our worker population and we're trying to assume some kind of representative sample that we're sampling. So if we take our most compliant workers or our oldest workers, they may not truly be representative of the whole's exposure profile. So random sampling is each subject has an equal opportunity of being part of your sampling routine. When we truly random sample, we random sample by person, by work location, and by shift. Or then we can do a systematic random sampling where we may choose a location or a process or a shift, but then randomly select the people out of that predetermined group. Worst case, with limited sampling funds or sometimes time, the concept is to pick the highest exposures at a certain point in time, but this does not take into effect the averaging of our workforce as a whole. So where do we sample? We already talked about personal sampling within a breathing zone, area sampling within the environment, or surface sampling for secondary contamination. Can also be a surrogate for dermal exposure. And then we're always doing our personal observations at one time when we're doing our sampling. So how do we sample? Well, it really depends on what we're sampling for. We'll cover this in more detail when we look at analytical methods. I'll stick pretty closely to the NIOSH methods, but you may be using other methods such as OSHA or EPA. Really, the important take-home message there is to be consistent across your methods. So if you're sampling for silica, use one method so it can be used comparatively. How many samples to take? Oh, the magic number. We don't know what the magic number is, but from the NIOSH Manual of Analytical Methods, greater than 29 per similar exposure group is typically has little statistical benefit. 7 to 9 samples, that's not people, but that's samples per similar exposure group, is a good starting point. It's usually not reasonable to make the number of samples directly proportionate to the number of workers. Another technique that's used is the square root of the number of workers within a similar exposure group is a way to give you a starting point as to how many samples to take. 7 to 9 is again a starting point, and we have to think about our time variable. Sometimes we have to take lots of samples because we can only sample for a short duration depending on the method, and other times we can only take one continuous sample because we need a lot of volume depending on the method. And we'll look at that certainly more closely in one of our next lectures. But always remember when you're counting how many samples to take to include our STELs, which should be run for 15 to 30 minutes if possible, given the sample volume, as well as the number of blanks which are defined in the standard. And although these aren't necessarily the number of samples we take when we have a blank, but we treat that blank like a sample, so it has to be part of our overall calculations of how much this sampling campaign is going to cost us. How frequently, again, this is covered further when we look at our strategy for sampling, but some general guidance at the beginning of each shift, throughout your shift, after significant changes in a work process, the addition or subtraction of some type of new agent. Continuously, of course, for confined space, toxic or oxygen deficient atmospheres, where exposure estimates exceed 3/4 of a standard throughout a shift, or when concentrations are greater than an action limit or half, we need to continually sample. There definitely is some subjective bias in there, but we'll look at this topic. We'll explore it further as we move on. This is our introduction to sampling. So what do we need to remember? Well, we have personal sampling and we have area sampling. Surface sampling is an area sample as well as a personal or observational method. We can do active sampling, actively drawing air through a pump, versus passive sampling, air being wafted over a dosimeter. The physical agent, the state of it, and the route of exposure will definitely help us determine our sampling protocol, when, how many people, which method we'll use. And it's always imperative to establish similar exposure groups because it'll help you with your sampling methodology. And a good rule, well, we won't use a rule of thumb, but a general rule would be the square root of n is a good starting point to the number of samples. Remember to include STELs in there, as well as worst case sampling during high output operations where a sealing may be included. Thank you very much. Have a splendid day.